In this session, we'll be seeing about a problem in MM1 infinite FIFO model. The first M standing for the Markovian arrival, the second M representing the Markovian service, 1 representing the number of server, infinite, the system capacity, FIFO, the Q discipline, first in, first out. The problem to be analyzed is as follows. The arrivals at a telephone booth are considered to be Poisson with an average time of 12 minutes between one arrival and the next. The length of the telephone call is assumed to be distributed exponentially with a mean 4 minutes. We have to find the following. Before analyzing the problems, we just take a look into what are going to be the basic things which we need to know. We have been given that the average time between one arrival and the next, that is the inter-arrival time, is going to be 12 minutes, but we know that the inter-arrival time follows an exponential distribution which has a mean given by 1 by lambda. So we know that this 1 by lambda is 12. So the mean arrival rate, which is the lambda, is going to be 1 by 12th of a minute. Secondly, we have been said that the length of the telephone call is assumed to be exponentially distributed. That is, the service which is available is also exponential with a mean of 4 minutes. So this exponential service, let us denote it by 1 by mu. This 1 by mu has been given as 4 minutes. Therefore, the mean service rate will be 1 by 4th of a minute. So now we will try to find the solution for the questions posed. Find the average number of persons who is waiting in the system. The expected number of persons in the system is what we need to evaluate. The expected number of persons in the system is given by the formula lambda divided by mu minus lambda. So this lambda is nothing but 1 by 12, mu which is 1 by 4, minus again lambda which is 1 by 12, makes it as 0.5 customers. The second question asked is, what is the probability that a person arriving at the booth will have to wait in the queue? So when we will have to wait? We will have to wait when the service is not immediate. That is, there is someone who is already there in the queue. So the probability we will have to wait is nothing but 1 minus probability that there are going to be no customers in the system. And what is this probability of no customer in the system? This is represented as P naught. So first we will see what is the formula for P naught. P naught is given by 1 minus lambda by mu. So putting it back in this original formula, we have it to be 1 minus lambda by mu. So this 1 and 1 cancels off, leading you to lambda by mu, which is 1 by 12 by 1 by 4, which takes the value 1 by 3. The next question asked is, what is the probability that it will take him more than 10 minutes altogether to wait for the phone and complete the call? So in such case, what will happen? We'll have to find the probability that the waiting time in the system is going to exceed the time t, which is given by the formula e power minus of mu minus lambda times of t. So now our question asks us, what is going to be the probability that the waiting time in the system is going to be more than 10 minutes? So this will give me e power minus, substitute the value for mu is 1 by 4, lambda is 1 by 12, and t we can substitute as 10, which is provided over here in the question. So it makes it as e to the power of minus 5 by 3. So estimate this using your calculators, which leads you to the answer 0.1889. The next question asked is, the telephone department will install a second booth when convinced that the arrival has to wait for an average of at least 3 minutes for the phone. By how much the flow of the arrival should increase in order to justify a second booth is guaranteed. So if there has to be a second booth, then the queue has to be in an overwhelming way. So they say that the second phase or the second form the second phone will be installed if the queue length, expected number of people in the queue, waiting time in the queue waiting time in the queue is going to be more than 3 minutes. Expected waiting time in the queue is more than 3. And we know the formula for expected waiting time in the queue, which is lambda divided by mu into mu minus lambda. So this has to be greater than 3. Okay, so let this new arrival rate required for to justify a second booth be denoted by lambda r. Let this lambda r be the required arrival rate to guarantee a second booth. So we have been given that lambda r divided by mu times of mu minus lambda r has to be greater than 3. So cross multiplying, we have lambda r to be greater than 3, and this mu is going to be 1 by 4. So 3 by 4 times of 1 by 4 minus lambda r. So this gives me lambda r is greater than 3 by 28. So how much has to be the increase? So the increase must be the new value minus the old value. So what is the new value for lambda which we have? The new value is going to be 3 by 28. And the old value for lambda, we know that it is 1 by 12. So if we take the difference of it, it has to be 1 by 42 per minute. And if it is guaranteed that the new arrival rate is going to be 1 by 42 per minute, then we can justify that the second booth will be installed. And the last question is, what is the average length of the queue that forms from time to time? So we need the length of the queue that gets formed, E of WQ, length of the queue that gets formed, provided the number of persons in the queue is going to be more than 1. So this is given by the formula mu divided by mu minus lambda. And this is nothing but 1 by 4 by 1 by 4 minus 1 by 12, which will be leading us to the answer 1.5%. So this completes a problem in our model number 1.